Okay, good morning, everyone, and welcome to the meeting of the Scientific Review Panel. I'd like to welcome everyone who's in their various locations and everybody who's on the web. Please note that the meeting is being recorded, and Arash Mohey is going to be overseeing our Zoom technical operations, and he's got just a brief announcement about our webpage and additional information. Arash, you want to say that now?
Thank you, Court. So the meeting is being recorded, and you can find the recording in a few days on our webpage dedicated for this meeting. You can find that webpage for the links that I'm going to put in the chat or from the QR code that is on the screen. On that webpage, you can find materials related to this meeting, including the slide deck that two of our presenters are going to be sharing today. Thank you, Court.
Thank you, Arash. So let's introduce the panel. Joe, can you start us off? Brief introduction for yourself. Joe, you're muted.
Did that do it?
Yep.
Okay, sorry. Thank you. I'm Joseph R. Landolf, PhD. I work at the University of Southern California. I'm an associate professor of molecular microbiology and immunology and pathology, and I'm a member of the USC Norris Comprehensive Cancer Center. And I've been here for many years. I've worked on the SRP for probably about 10, and I also work on the CIC. And I do research in chemical carcinogenesis, morphological neoplastic transformation by carcinogens in cell culture.
Thank you, Joe. Paul?
Me?
You.
Hi, Paul Blanc. I'm a professor emeritus at UCSF and am continuing on the SRP only until such a time as the appointment replacement is in place. And I'm assuming that this would probably be my last meeting.
We're hopeful, Paul, but things are moving slowly.
Yeah.
Thank you, Paul. Karen?
Good morning. I'm Karen Messer. I'm a professor of biostatistics at UCSD and director of the biostatistics group at Moore's UCSD Cancer Center.
Thank you, Karen. Ahmad?
Good morning, everybody. I'm Ahmad Basaratinia. I'm a professor at the Department of Population and Public Health Sciences at University of Southern California here in Los Angeles, and I have been a member of SRP for the past 5 years.
Thank you, Ahmad. Mike?
Good morning. I'm Mike Kleinman. I am a professor in the Department of Environmental and Occupational Health at UC Irvine in the brand new School of Population and Public Health.
Nice. Thank you, Mike. Beata?
Hello, everyone. I'm Beata Ritz. I'm a professor of epidemiology at UCLA, School of Public Health, in the Department of Epidemiology, Environmental Health, and Neurology. And my focus is on pesticide and on air pollution research.
Thank you, Beata. And I'm Cor Anastasio. I'm a professor in the Department of Land, Air, and Water Resources at UC Davis and the chair of the panel. I appreciate everybody coming, especially our 4 members whose terms have officially ended. Paul, Mike, Beata, and Kathy. So all of their terms are ended. We really appreciate them participating today. And we're trying to get replacements, but it's been a very slow process. 2 items in today's meeting. The first is going to be a review of the isoprene cancer inhalation unit risk factor, the IUR. And the second will be an informational item from OEHA on computational toxicology and their new approaches for developing health guidance values. And then we're going to have some administrative matters, including a formal send-off for Paul Blanc, longest serving current member of the SRP. All right. So move to the first item. The isoprene cancer inhalation unit risk factor. So the staff from the Office of Environmental Health Hazard Assessment, OEHA, are going to present a draft document summarizing the development of a cancer potency factor and inhalation unit risk factor, IUR, for isoprene. Cancer IURs are used to estimate lifetime cancer risks associated with inhalation exposure to a carcinogen. OEHA is required to develop guidelines for conducting health risk assessments under the air toxics hotspots programs, which is part of Health and Safety Code Section 44360B2. In response to this statutory requirement, OEHA developed a draft IUR for isoprene. Workshops and comment period for the document were offered from February through April of 2024. No public comments were received. More information regarding the document can be found at a long website, https. I'm not going to read the whole thing. It's on the OEHA website under isoprene. So I'd like to now introduce Drs. Darren Dodge and Kenneth Clock, who are staff toxicologists, and the item leads from OEHA. Darren and Ken, the floor is yours.
Okay, thank you, Court. As Dr. Anastasio said that I'm a co-author of this document, and I'll be presenting it today. Okay, wait, next slide. Okay, this is the structure of isoprene. It's a diene containing 2 carbon double bonds with a methyl group on the second carbon. It is also known as 2-methyl-1,3-butadiene. It is the 2-methyl analog of 1,3-butadiene, which is a fairly ubiquitous compound also found in urban air, and it is a known carcinogen. Next. Isoprene is a colorless liquid with a mild petroleum-like odor. It is soluble in many organic solvents. The solubility in water, though, is 642 milligrams per liter, which in pharmacology references is considered poor aqueous solubility. It has a boiling point of 34 degrees C or Celsius, which is equivalent to 93.2 degrees Fahrenheit. The vapor pressure is 550 millimeters mercury or torr, and this is high enough vapor pressure to be considered a VOC or a volatile organic compound. The unit conversion is 1 part per billion, is equivalent to 2.79 micrograms per cubic meter. Isoprene is naturally emitted by plants and trees. It is produced endogenously in humans and other mammals. It occurs as a byproduct of the thermal cracking of naphtha, and it is used to make synthetic rubber for vehicle tires. Other sources of isoprene include biomass combustion, wood pulping, tobacco smoking, exhaust from turbines and automobiles, and it is found in wildfire smoke. Emissions of isoprene in California. In 2017, it was 186 tons per year, primarily from mobile sources. There were 12 facilities in the CEDARS database that emitted significant levels of isoprene, although there's probably many more facilities that do release isoprene. CEDARS stands for the California Emissions Inventory Data Analysis and Reporting Program. Urban air levels of isoprene correlate with other chemicals such as benzene found in vehicle emissions. Air concentrations reported in California in the South Coast Air Basin or Los Angeles area. The concentrations were 0.5 and 1.8 micrograms per cubic meter respectively. That's the average and maximum respectively. In the San Joaquin Valley, it was 0.1 was the average and 0.8 was the maximum. And that's in micrograms per cubic meter. In exhaled breath, the steady state concentrations are 195 to 371 micrograms per cubic meter in adults at rest. This represents the 25th to 75th quantile range. I'll add that in infants and children, the exhaled breath concentrations are less, generally 70 micrograms per cubic meter or less. The cancer classifications for isoprene in the California Proposition 65 program, it is listed as a carcinogen since 1996. The International Agency for Research on Cancer, or IARC, categorizes it as a possible carcinogen or possibly carcinogenic to humans, group 2B. And the United States National Toxicology Program, or NTP, categorizes it as reasonably anticipated to be a human carcinogen. Metabolism of inhaled isoprene is similar in humans and rodents. This primarily occurs through oxidative metabolism via P450 enzymes to epoxide intermediates. This is followed by hydrolysis, conjugation with glutathione, and further oxidation of diols formed via hydrolysis. The main urinary metabolites in rodents are 2-methyl-3-butene-1,2-diol and its glucuronide and vinyl lactic acid. The carcinogenicity of isoprene is thought to be related to the formation of oxidized reactive metabolites, including monoepoxides, a diepoxide, and diol epoxides. There were no occupational studies that looked at the carcinogenicity of isoprene. However, we do have 3 sets of rodent carcinogenicity bioassays from which to examine. The first was by NTP, National Toxicology Program, which came out in 1995. This is a 1-year stop exposure study in only male rats and male mice. Exposures were for 6 months, 6 hours per day, 5 days a week, plus a 6-month clean air period, following which the animals were necropsied and examined for tumors. There were 5 exposure groups, or 5 isoprene exposure groups per species, and 1 control group. And there were 30 rodents per species per group. The next study was by Plackey et al. And came out in 1996. This was a 2-year study in male and female mice. The isoprene exposures were for 80 weeks, 8 hours per day, 5 days a week, with sacrifice at 105 weeks. There were 5 isoprene exposure groups for male mice and 1 control group. However, for the female mice, there were only 2 isoprene exposure groups and 1 control group. There were 50 mice per group per sex. The final study was by NTP, came out in 1999. This was a 2-year study in male and female rats. As you might know, NTP often also examines the carcinogenicity in male and female mice as well. However, the NTP felt there was enough information on mice by this time, so they only looked at the male and female rats. Exposures were for 104 weeks in the rats, 6 hours per day, 5 days a week. There were 3 isoprene exposure groups per sex, and there was 1 control group each. There were 50 rats per group per sex. I'll go over the results, the tumor incidence results here first, starting with the NTP 1-year stop exposure study. In male rats, the only treatment-related tumors were in the testes. This was the adenomas. There was only a marginal increase in adenomas with pairwise comparison with the control group. However, there was a positive trend for this tumor type, so the NTP felt this was likely treatment-related. There was a higher tumor incidence in the male mice, however, from this NTP 1-year stop exposure study. There was an increased incidence of tumors in 1 or more treatment groups in the liver, lung, forestomach, and Harderian gland. Now, this table is simplified a bit. We show the liver adenoma and carcinoma together, combined, and as well as for the lung, adenomas and carcinomas, and the forestomach squamous cell papillomas or carcinomas. We looked at the combined benign and malignant tumors together for a tumor site. This is generally how we determine the cancer risk of a chemical. The combined benign and malignant tumors. There was a positive trend for all 4 of these tumors at all 4 of these tumor sites. For the last set of tumors there, or tumor in this table, the Harderian gland, there was only an increase in the adenomas. There was no effect due to in the Harderian gland concerning the carcinomas. In the next study by Plackey et al., this was the 80-week exposure study in male mice and mice and female mice. They looked at the same strain of male mice as the NTP stop exposure study. They found tumors at the same tumor types as that found in the NTP stop exposure study. That is in the liver, lung, forestomach, and Harderian gland. However, we show this information separate for the adenomas and carcinomas for the liver and lung. And this is because Plackey et al. Did not provide information in their study in which we could show the combined benign and malignant tumors at these tumor sites. So we show it separately in this table. In the forestomach, there was a increased trend for squamous cell carcinoma, although the increase was marginal in terms of incidence. In the Harderian gland, there was an increase in adenomas, increased incidence at the 3 highest exposure groups. Carcinomas, again, this was a marginal increase here. In the female mice from the Plackey et al. Study, there was an increased incidence of adenomas in the Harderian gland and pituitary gland in one or both isoprene exposure groups. There was no increase in carcinomas at either of these tumor sites. In the middle row there, the spleen hemangiosarcoma, there was a marginal increase at the highest dose of 70 parts per million. Even though this was not statistically significant with pairwise comparison with the control, the authors felt this was a treatment-related effect. In the final study, the 2-year NTP bioassays in male and female rats, the information here includes both the male and female rats in this table. In the male rats, there was a increased incidence in one or more exposure groups in the male kidney renal tubule adenoma or carcinoma, in the mammary gland fibroadenoma or carcinoma, and in the testes, there was an increase in adenoma. As you might notice, there are 2 sets of incidence data in each cell of this table. The first or top set of incidence data, that's the overall incidence. So it's the number of tumors over the number of animals exposed. The bottom set of incidence results in each cell, that is the effective tumor incidence. It's bolded and italicized in each cell. The effective tumor incidence is the number of animals alive at the appearance of first tumor. This is specific for each tumor site. This is the information, if it is provided in the study, that we use to determine cancer risk. So if this information is available, in other words, this is what we use to estimate the inhalation unit risk. Now, in the female rats, there was an increased incidence in mammary gland fibroadenoma in all 3 exposure groups. However, the incidence was essentially the same for all 3 exposure groups. So it hit somewhat of a plateau starting at the lowest concentration. The incidences were essentially the same as it's 35 out of 50, 32 out of 50, and 32 out of 50, going from 220 to 7,000 parts per million. So this was likely a treatment-related effect. However, because of the plateau effect, a positive trend was not attained. Okay, on this slide, we have a summary of the genotoxicity results. Studies on the genotoxicity of isoprene have been conducted in various in vitro and in vivo systems. In human cell lines, including peripheral blood mononuclear cells, leukemia cells, and hepatocellular carcinoma cells, isoprene in its monoepoxides were shown to cause DNA damage using the COMET assay. In vitro assays for bacterial mutagenicity were largely negative when isoprene in its primary metabolites were tested, but was positive for the metabolite 2-methyl-1,2,3,4-diepoxy butane. In mice, in vivo inhalation exposure to isoprene induced micronuclei formation and sister chromatid exchange in bone marrow cells. We also evaluated 3 publicly available models, PBPK models, which stands for physiologically based pharmacokinetic models. We were interested in seeing if we could use this information to improve our dose metrics, such as the rate of metabolism of isoprene to an epoxide. While these models were excellent in terms of the specific goals they were attempting to achieve, the models did not provide enough information for pharmacokinetic extrapolation from rodents to humans. Therefore, we relied on our usual applied dose or inhaled concentration of isoprene as the dose metric for estimating cancer potency. Mike? So this is our overall cancer hazard evaluation. We have no epidemiology studies from which to determine the carcinogenicity of isoprene. Therefore, we relied on the 3 available rodent long-term inhalation bioassays. These rodent bioassays found that isoprene was carcinogenic in multiple species and induced tumors at 1 or more sites in rats and mice. There were positive genotoxicity studies, primarily in vitro DNA damage assays and in vivo chromosomal damage assays. Isoprene is also structurally related to the compound 1,3-butadiene, a known human carcinogen. Okay, so that's the incidence data. The other part that we need to use in terms of determining the cancer potency of isoprene is the average daily dose. So we convert the air exposure concentration of isoprene to an average daily dose in milligrams per kilogram body weight per day. And this is done within the equation in the slide. ADD is equivalent to or equal to the IR, or inhalation rate, times concentration divided by the body weight. So C, or the concentration, is time adjusted to an annual average. And that is 6 or 8 hours per day, depending on the study, divided by 24 hours. And this is multiplied by 5 days per week, divided by 7 days. The body weight is the body weight of the, or average body weight of the animal over the period of exposure. An inhalation rate is a species-specific calculation. The equations are shown here at the bottom of the slide for rats and one for mice. So these are the average daily doses in mice from the Plackey et al. Bioassays. In the male mice, we have 5 exposure groups, but if you recall, for the female mice, we only had 2 exposure groups. And these are the average daily doses for rats from the NTP bioassay for males and females. As you might have noticed already, we do not have the average daily doses from the first study, the stop exposure study from NTP. And this is because that study was only for 1 year. If we can use or have access to lifetime studies in rodents, that is what we use to determine an inhalation unit risk. Since we had that information in 2 studies, Plackey et al. And NTP 1999, we didn't go any further with the 1-year stop exposure study. So to determine the cancer slope factor, we use the US EPA multi-stage cancer model in the benchmark dose software. We used a benchmark response rate of 5% tumor response to calculate the benchmark dose, which is the BMD. The 95% lower confidence bound on the dose producing a 5% tumor response is the BMDL05, and this is used to calculate the cancer potency. So the cancer slope factor is equal to 0.05 divided by the BMDL05. Now, in male mice and male rats, there was multiple tumor sites. So the combined tumor potency was determined for these animals using the USEPA multi-site model. So we determine cancer slope factors. Let's start with the Plackey et al. Data. We determine cancer slope factors in the liver, lung, and Harderian gland, these tumor sites, both individually and combined using the multi-site model. We also did this in the female mice, the pituitary and Harderian gland adenomas, both individually and combined. However, we did not use the female mice information to determine a final cancer slope factor because only adenomas were increased in female mice. In other words, benign tumors. In the NTP study in male and female rats, in the male rats, we looked at the cancer slope factors or calculated cancer slope factors for kidney, mammary gland, and testes individually and combined using the multi-site model. For female rats, there was only one tumor site, and this was mammary gland, and only fibroadenomas were increased. Since these were benign tumors, we did not go any further in terms of calculating cancer slope factors with that information. So this is the graphical output of the benchmark dose software. In this graph, we show the renal tubule adenoma and carcinoma combined in male rats from the NTP study. So along the bottom row or the x-axis, that is the lifetime average daily dose in milligrams per kilogram day. And along the y-axis on the left side, that's the tumor incidence. The orange triangles is the incidence data, and the benchmark dose software draws a line to this data, and that's the blue curved, slightly curved line. The benchmark dose, 5% above control, that's the dotted vertical black line that falls in around 500 milligrams per kilogram day. The yellow dotted vertical line, that is the lower confidence bound, and that falls at about 295 milligram per kilogram day. So the intersection of the yellow dotted line, the lower confidence bound, and the horizontal gray line, which is the 5% incidence above control, that intersection is where you find the where you get the cancer slope factor. That's the dashed green line that you see, straight green line that starts at that intersection and goes to the control level. So that is our cancer slope factor from which we derive the, well, that's where we derive the cancer slope factor. And this is the graphical output from the benchmark dose software for mammary gland fibroadenoma and carcinoma combined in male rats. And this is the graphical output from the benchmark dose software for the testicular adenomas in male rats. And what's interesting in this particular graph is the control group had a quite high incidence rate. This was close to 70% incidence in the controls. However, with exposure to isoprene at the highest concentration here, you get an increased incidence of almost 100%. So now we extrapolate the animal cancer slope factors to a human cancer slope factor. This is done by multiplying the cancer slope factor of the animals by the ratio of human to animal body weights raised to 1/4 power. And this is expressed in units of milligram per kilogram day to the -1. This interspecies scaling factor accounts for pharmacokinetic differences such as breathing rate and metabolism, but also takes into account pharmacodynamic considerations such as tissue responses to chemical exposure. So in this table, this is the benchmark dose results, including the calculated human cancer slope factor in the last column on the right. So in this table, we show the multi-site data in male mice from the Plackey et al. Study, the generation of the BMD and BMDL in the benchmark dose software. So the BMD is 28.8, the BMDL is 23.69. This results in an animal cancer slope factor of 2.11 times 10 to the -3. And using the equation we just showed in the previous slide, we calculated a human cancer slope factor of 1.47 times 10 to the -2. In the NTP study, this is the multi-site results in male rats. The resulting human cancer slope factor is slightly higher. It's 1.88 times 10 to the -2. It's bolded in this table. So this is actually the number from which we determine the inhalation unit risk, or IUR, for isoprene. Now, the NTP results here, the cancer slope factor is slightly higher in the rats compared to the mice, but we had some reservations anyway for using the Plackey et al. Study. So the Plackey et al. Mouse study had limitations in terms of the combined adenoma and carcinoma incidence was not reported for liver, lung, and Harderian gland tumor sites. Therefore, modeling was only performed with the adenoma incidence data. In addition, no data on individual survival or appearance of first tumor was supplied in the study, so we could not determine the effective tumor incidence. Thus, we used the overall incidence rate to determine the cancer slope factors. Now, this information doesn't mean we can't use it to determine an IUR. It's just that we had all this information from the NTP study in the rats, so that's what we used to determine the IUR. So that's this final step. So again, the isoprene IUR is based on the male rat data in NTP. And this equation is the IUR is equivalent, or it's equal to the cancer slope factor in humans times the breathing rate in humans, which is 20 cubic meters per day. This is divided by the body weight in humans, 70 kilograms, and multiplied by a conversion factor going from milligrams to micrograms. The resulting IUR is 5.4 times 10 to the minus 6th. This is in units of micrograms per cubic meter to the minus 1. Now, to explain or show what this number means, lifetime adult exposure to 1 microgram per cubic meter isoprene results in an extra cancer risk of 5.4 cases in a million. So at this point, we would present the public comments in our responses, but as court has already pointed out, there were no comments that came in during the public comment period. We did hold workshops, though, in Southern California and Northern California during the public comment period. And that concludes my presentation.
Great, thank you very much, Darren. So the two SRP leads on this IUR are Ahmad and myself. So Ahmad, would you like to go first?
Sure. Here. Well, first of all, I want to recognize the work of the authors and contributors to this report, including the presenter Daryl today. This is a well-prepared and nicely written report. Seems to have covered most of the relevant literature. It's used established methods to derive a cancer slope factor and IUR to estimate cancer risk for isoprene in humans. The results are presented clearly and discussed very well, and conclusions are made accordingly. I have a few general comments and some specific comments that I can share here. Firstly, as it was mentioned during the presentation and described in the report, humans are exposed to isoprene through multiple sources. We have occupational exposure in certain industry workers. We have environmental and dietary sources of exposure. We have lifestyle exposure, for example, through tobacco smoking. We, of course, have endogenous exposure to this chemical. So human exposure to isoprene is substantial and variable. With this in mind, it's quite surprising to see that there was no human study or epidemiologic data in this report. The CSF and the IUR were derived exclusively from two animals studied, one inhalation experiment in mice and the other in rats. I'm assuming that there is either no epidemiologic data on isoprene or the available epidemiologic data are not of adequate quality. Either way, it would be helpful and certainly important to underscore this fact and explain why no human study or epidemiologic data were used for risk assessment in this report. There was a one-line sentence somewhere in the report, I think it was in page 5. There was a mention that there is no carcinogenicity data for isoprene in humans. I saw that Daryl's slide also contained a bullet point on this. My recommendation would be just to create a subheading in the introduction section of the report and provide this information upfront and explain why only animal data were used to derive CSF and IUR. Along the same line, I think it will be helpful to discuss the challenges of exposure assessment for this chemical in humans, especially given the multi-source nature of exposure and the lack of consensus on how and where to measure isoprene or its metabolite in human samples. For example, in occupationally exposed individuals who also have endogenous exposure to this chemical, as well as exposure through other sources, definitely exposure assessment must be very complicated. My second point has to do with the way that the CSF was calculated for rodents and then extrapolated to humans to derive the IUR. It's proven that there are major differences in pharmacokinetics of isoprene between humans and rodents. These differences can reach orders of magnitude depending on the endpoints measured. My understanding from reading this report was that interspecies differences were not accounted for in this report, and there was no adjustment made when converting the CSF from animals to humans to derive an IUR. Daryl, in one of his last slides, I think slide 25, mentioned something different in the formula that he presented. He said that this formula accounts for interspecies difference. So it will be helpful to provide some clarification on this. If it was not adjusted for, definitely some justification as to why you believe that there is no need to adjust for interspecies differences, considering the significant pharmacokinetic differences between humans and other mammals, including rodents. I think there was one mention of this somewhere at the last part of the report. I think it was the last page, page 36 of this report, but probably it needs to be more clear. My next point is on the statistical analysis in table 2A and 2B and table 3. It is indicated in the text and footnote of this table that pairwise comparison between the exposed and control groups were made by one-tailed Fisher-Exact test. Looking at this data in this table, the directionality of effect is not one-sided. By way of example, in table 3 in page 13, if you look at last row from the bottom, you see that the incidence rate for all exposed groups are lower than that in the control group. The same is in table 2A, page 9. You can see it in the second and third row. So I'm not a biostatistician, but as far as I know, to apply a one-sided test, you need to make an assumption that the relationship can only go in one direction. Looking at this data, it doesn't seem that this assumption can be made, and I'm not sure what the rationale is for using a one-sided test instead of a two-sided test. So it will be helpful to clarify what the justification is for the analysis performed for the data in this table. I think a short clarification in the text will do. I would imagine any guidelines or recommendation that you might have used must have a provision for cases where there is a bidirectionality of effects like data in your table. Probably Dr. Messer-Karen has more expertise on this. Definitely, she knows more than me, and she can later comment on this and help us better understand the appropriateness of this test. And just a couple of minor comments. I think it is important for all these technical support documents, including this present report, to have a designated section within the main text with a subheading where the research strategy and time frame of coverage is stated. It will help the readers to understand how comprehensive and how up-to-date these reports are. I saw a line in preface where it reads, publicly available documents and report through July 2023 were reviewed. I think it will be more helpful for reader to have this information and specific information about search strategy, search engine that was used. Was it PubMed, Medline, Embase, Google Scholar? What search term was used? What type of publication were considered? And definitely the start and end of coverage. And my last point is the footer in all pages contains a statement that reads, please do not cite or quote. I'm assuming that this will be removed once the report is finalized. And that's all I have. Thank you.
Thank you, Ahmad. So I'm going to put Karen on the spot for a second about this one-tailed versus two-tailed Fisher test. Karen, can you weigh in on that?
Yeah, first I want to echo that I thought the report was nicely presented and clearly done. I think a one-tailed test is fine here. The rationale for the one-tailed test is really more the intent of the analysis than whether the data show trends in one direction or another. And here, the intent of the analysis is to detect an increasing signal. If for some reason the the compound being investigated is protective against cancer, where you would see a decreasing signal, well, that's not of interest in this setting. It wouldn't lead to air quality standards. But if there's an increasing signal, that's where you would find a public health need for air quality standards. Since a one-sided test gives you more power and the data are necessarily limited in these animal studies and indeed in epidemiologic studies, I think it's a good idea to use a one-sided test. I agree. There might be a comment in the report about why a one-sided test is used. Does that help?
Yeah, that's great.
It does.
Court, I wonder if I could comment specifically on this one question.
Sure.
It would seem to me, however, as a nuance to this, that in those analyses for which there was no positive, statistically significant test for trend, one should not carry out pairwise comparisons. Because really the test for trend is you're asking, is there overall a monotonic dose response? And if there isn't a monotonic dose response, why would you be doing multiple testing to compare various levels in a pairwise way with the control? I'm being a bit of a purist, but it could even make your lives simpler.
Yada, you have a response to that?
Yes, I would have a problem with the ceiling effect then, because you're throwing out all of those results, right? There was one that showed an increase that was kind of similar at every level of exposure. And I think that's something we should consider. And as I understood, the trend test did not show anything.
Thank you. Okay, I'm going to give my comments and then we'll open it up to the rest of the panel. So I just had very few comments as well. I thought the document was well written. I thought it was well justified. I thought everything worked out very smoothly. Just some minor comments. One was on line 45. You got a melting point that's above the boiling point, which is not physically possible. So I wonder if you're missing a negative sign on the melting point or one of the numbers is wrong. So that's one item. Second item was a question I had. So on line 524, you talked about the process for doing the risk assessment. And in step 4, you talk about intercurrent mortality. And I'm just not sure what that is. Could you explain it to me now?
Dr. Ken Clock, would you like to explain that? Take that one on.
I can give it a shot. So basically what we're, intercurrent mortality, it's an expression which is supposed to stand for mortality that is not due to the chemical being investigated. I'm sorry, it's not due to tumor formation in the chemical being tested, but to just regular toxicity. And so what that does is it creates a situation where you have animals that are being removed from the denominator of the estimated cancer potency. And so you need, when possible, you try to adjust for that.
I see. Thank you. The third comment or question I had was about combining incidents of different cancer types or tumor types. So I know in one case you looked at a tumor type that included both benign and malignant tumors. And you did a risk assessment on that, but then there was another case where there were only benign tumors, and so you said, okay, we're not going to consider that, and that makes sense to me. You also do a combining of tumor types that if they have, I think it was either the same tissue or the same cell type. But I'm wondering, why don't you combine all the tumor types that were malignant? You would think that, any incidence of cancer would count towards the overall possibility of getting cancer in the human population. So why not combine all incidences across cell types, across tissue types?
Well, we do that with the multi-site model, US EPA's model. If it's believed that the adenomas and carcinomas at a cell site are treatment related, the increases in incidence, then we combine it. So it's adenomas or carcinomas combined. So that's what we plug into the multi-site model.
So okay, I guess I missed that distinction. And so the multi-site model is multiple tissue types or multiple cell types.
Yes, yes.
Okay. Somehow I missed that in the description. Okay, thank you. Well, that's great. The last thing I wanted to say was give some compliments to the authors, because there were a lot of kind of mostly style points that were made that I thought were great, and we've been talking about it over the last few years. So I just wanted to thank you for putting line numbers in there. That was very helpful. I'd like to thank you for putting p-values and not just having, say, bold if it's p less than 0.05. I thought the comparison with the derived IUR for the TCEQ numbers was very helpful to me. And to know that EPA doesn't have an IUR, that was helpful information. So thank you for making that comparison. I also thought the IUR comparison with butadiene was helpful to see the relative toxicity of isoprene to butadiene, and they're at least ballpark. And then finally, the BMD plots and the appendices, I always find it helpful to see the plots of the data and the fits. So we get some sense of, is that a reasonable fit or not? So thank you for including those as well. Those were all my comments. So I'm just going to go in order of the video boxes on my screen to see if other panel members have comments. Joe, any comments from you?
I echo everybody's statements that it's an excellent document. A lot of work went into it. I had two questions. One is, for the two primary reviewers and the author, what do you think about isoprene in a relative cancer potency toxicity comparison? Is this something we should really worry about? Is it higher on the priority list of OEHA and the Air Board? What are your thoughts there? And then I'll have another one after they answer that.
Thank you, Dr. Landolf. Yeah, because of its structural similarity to butadiene, there was, and its ubiquitous nature, exposure, there was interest in developing an IUR for isoprene. That's pretty much the main reason Cal EPA wanted to develop an IUR for isoprene. As you notice, the cancer potency of isoprene is, in comparison to 1,3-butadiene, is not as high. However, we feel that any incremental increase in isoprene, other carcinogens that people are exposed to, will increase the cancer risk. So it's good to have this an IUR for this compound, because when we do an assessment, an overall assessment to what people are exposed to, we should include all the carcinogens that we know about in determining cancer risk.
And that's would you, on the scale of what you've already done, the compounds that you've already measured IURs on, where does it fit quantitatively?
Well, isoprene doesn't appear to be as a potent carcinogen as 1,3-butadiene and some other diesel exhausts, for example, that people are exposed to in urban air. So overall, it's probably not as big as a concern as the main contributors.
That answers it. Thank you.
So on that topic, the IUR was what, roughly 5 times 10 to the minus 6 per micrograms per cubic meter. And the ambient data was coming in at around 1 microgram per cubic meter. So you've got a kind of a general urban population risk of 5 in a million. Is that above the threshold where the hotspots kicks in and they start to look at point sources and try to understand risks around those sources?
Those are sort of general urban air levels of isoprene. We probably don't have a lot of data on facility emissions that might release isoprene. We do know that there are measurable levels of isoprene coming from petroleum related industries, and the level of isoprene could be considerably higher than what you find in just your general urban air. So we have to take that into consideration.
Yeah, it's a tricky compound because the lifetime is short, right? It's a few hours in the atmosphere, but there are also enormous biogenic sources. So it's really a tricky risk assessment, which is, beyond the, risk management really. So it's beyond the scope of the IUR document, but it's something that risk management needs to consider. Yeah. Joe, any other comments?
Yeah, just one quick one. What is the philosophy of the SRP in terms of what we should put our most strength into looking at? Obviously, we've got, millions of compounds we could look at, but we don't have the time or the money to do that. Today, what are the top 5 you're focused on? What are you really serious about in terms of regulation, generating data that can lead to useful regulation and mitigation?
So this is a question for WEHA. So Joe, I'm trying to get clarification. Are you asking Darren and company what their top toxicant targets are for health guidance values?
Yeah,
moving-
that would be fine, just fine.
Yeah.
Hi, this is Dr. Rima Woods. I'm the chief of the air toxicology and risk assessment section. And we work closely with CARB on the hotspots program. And typically our top priorities are set in conjunction with CARB. So it's a combination of high emission compounds that CARB is seeing, and then we combine that with information from what we know about toxicity. So there are a few chemicals that we are working on currently. Am I allowed to say them? No. So yeah, so we have a few risk assessments in the works. We are working on ethylene oxide, which we have brought to the SRP previously. Also a few other that we may be working on assessments in the future. So I would check in with CARB if we're okay to mention any of those. Okay. Okay, great. Just wanted confirmation. So acrolein is one that we're currently looking at, and methylpyrrolidine is another compound that has sort of floated to the top of the list. And also 1,4-dichlorobenzene is a compound that we've been working on for a non-cancer value, which should come to the SRP fairly soon.
Thank you very much.
Mhm.
Thank you, Joe. Paul, comments?
Let me start off with the epidemiologic question, although Beatriz may also have comments. But clearly, there's epidemiologic data about the synthetic rubber industry, pro and con. And in fact, the European document, which you refer to, and which I think your document is highly influenced by, the European Union document, has a far more extensive discussion of why there is not epidemiologic data that looks solely at isoprene, but there is epidemiologic data that has looked at synthetic rubber trade. So I think it would be actually more useful for you to look at their language on that and perhaps expand your statements by a couple of sentences. But the one thing they didn't do either was to say whether that epidemiologic literature, which can't be interpreted easily for any one of the components in the industry, suggests that there's cancer in the industry or not. That would be highly interesting, even if you couldn't say what the culprit was. So I suggest you look at that wording, and also specifically is there literature for mixed exposures that's positive. In that vein, the Europeans, as you noted, upped their categorization from their equivalent of 2B to 1B, carcinogenic in animals. And the IARC evaluation was done 30 years ago, I think, before these NTP studies. Do you know, or can you easily find out, is a second look at isoprene on the IARC agenda? Is this a chemical they're actually working on now?
Thank you, Dr. Blanc. This is Darren Dodge. I did look to see if IARC was doing any investigations further into isoprene, and I didn't see anything in their future plans regarding isoprene.
And on the other, on the epidemiologic front?
No, I don't believe so.
No, I
This was just
mean,
from.
what do you think about language which expands a bit on the statement there are no epidemiologic data?
I agree with that. We will add that to the document.
Now, maybe, Beat, do you have a specific comment on the epi of isoprene of the synthetic rubber industry? Because it's not, I'm not a
Yeah,
deeply.
I'm not an expert either, but IAC has written on the rubber industry. There's a monograph, but I think it's pretty old. It's 1987. I just looked it up.
Yeah.
But
Yeah.
they looked at the whole industry, and that's probably useful.
The another technical question I have for you is that in your multi-cancer model, you do include the Harderian gland tumor endpoint. That's correct?
In the male mice,
In the male rats, I would guess, because that's what drives you. And both, I think it was commented on in both of both species, no?
yeah, that was a tumor incidence that increased in male mice. The adenomas, there was a statistically significant increase in the 3 highest doses. But for carcinomas, there was not.
So does that mean it didn't make it into your multi-cancer model?
This was the Plackey et al. Information, which we ultimately didn't use to determine an IUR, but we
Okay.
we did include it in a multi-site analysis.
I don't know if you want in the text or not to comment on some of the issues that relate to Harderian gland as an endpoint. It may be a moot point since from what you're saying, it was not in the rat data. So I didn't remember offhand which ones it was in, because obviously it's not a gland that exists in primates as far as we know. So, and is some commenters, say it's a kind of more sensitive endpoint, which is interesting in light of the adenomas. But I mean, it's a very small point, so I just wanted to bring it up and clarify. To me, more salient issue is the metabolism of the isoprene, since you argue convincingly that it's the metabolites that are carcinogenic, and you're particularly suspicious of one metabolite. I understood that correctly?
Well, there is genotoxicity data for, I believe, the diepoxide
Right.
metabolite. And I guess there is some agreement that that could be the most carcinogenic metabolite of isoprene. But we're talking about at least 4 different
Right.
epoxides that could be generated during metabolism of isoprene. And any one of those could be the prime culprit, where it's just not known.
Okay, but your comments on CYP2E1 is the P450 that is most important for metabolism to all of the epoxides?
Did you?
I could jump in here if you want.
Okay, sure, go, Ken.
It seemed so. We had reviewed a number of studies early on in the preparation of the document, where the researchers specifically attempted to ferret out which isoenzymes were responsible primarily for epoxidation of isoprene. And that's what they found, that it was primarily the 2E1 isoform, which was creating most of the epoxides. It wasn't exclusive though, but it was
Okay, but it's the
primarily
most important.
Yes.
So one of the problems with the figure, which only refers to P450 generically, as opposed to the paragraph of text that follows the figure, which highlights 2E1, is there's no footer in the table, in the figure, I'm sorry, which says when we say P450, it most likely is the isoenzyme. The isoenzyme that we're concerned about is CYP2E1. So I think it would be even clearer to whoever reads this that that's the isoenzyme that is relevant to the figure, which only generically talks about P450 in all of the arrows. And the reason I say that is, A, in this era, to simply talk about P450 is quite antiquated. And secondly, we know a lot about inducers of CYP2E1. And since if that is responsible for the carcinogenesis of this chemical, then, and if we want to make any comments about vulnerable populations, then that could be highly relevant. And the strongest known inducer of that isoenzyme is ethanol ingestion. And yet that wasn't mentioned in the report. I just think since we, in other work that OEA has done, we give consideration to vulnerable populations, I think it's worth alluding to, in my view. It wouldn't change any of your analyses. It just has to do with some text additions. I don't know if you would feel comfortable editing the text in that light.
No, I think you're correct, Dr. Blanc. We can add some language like that.
And then just to clarify, where you talk about anthropogenic sources of isoprene, but in those sentences you don't talk about the industrial synthetic rubber production. Did you mean anthropogenic other than industrial?
Are you referring to a slide? I'm sorry.
No, it's in your text, in your body. It's very early in your text, your introductory information about this chemical and what it's used for and where it comes from. And we don't have to belabor it here, but would you go back and look over it? I'm not sure that the text is as lucid as it might be in that regard.
Okay, yeah, sure, we can clear that up.
And also, just not to be a stickler, but isoprene is used. Yes, it is important for tires, but just that's not the only thing that synthetic rubber is used for, and so it's a little bit telegraphic in that. I mean, just with a few more words, you can say "and other end products," because it really oversimplifies, I think, where this is used industrially. I think the European document would help you. I would go back to that if I were you. And similarly, when you talk about it's released naturally, well, it was even in one of your slides, by vegetation and trees. I mean, trees are vegetation, so careful about the wording, but it's I was sort of shocked when you, surprised, you said in the main text, you say something like moss and ferns and trees. And I said to myself, well, so you mean no other plants? Bushes don't matter, shrubs don't matter, which I think is probably not true. So just, the wording, just as you said, including especially trees, but, obviously it can't be just trees, right?
Yes, we'll clear that up as well.
Okay. Those were my takes as I read through the thing.
Great, thank you, Paul. Karen, comments?
Yeah, thank you. My comments are similar to those of my colleagues. So from a technical point of view, I thought this document was well written, well explained, well presented, well justified. No major technical flaws, but it felt like we were reading a technical assessment in isolation without understanding its context, without a good understanding of the need for assessment of this compound, especially given the introduction where it seems to be ubiquitous with these large, both natural and human caused sources that are very dispersed. So it was a little bit, it just raised the question in my mind, as in some of my fellow reviewers, why this was prioritized for the hotspots assessment. What's the motivation? What's the opportunity for risk reduction if an IUR is established? Given that there were no descriptions of point sources or human exposure. So I guess my comment's quite general, following on the more specific comments of my colleagues. This is the report that I've read so far that seems to be most lacking in that kind of context. All the prior reports we could read some epidemiologic data that raised concerns and some descriptions of industry point sources where or situations where workers might have extremely high exposures. But none of that came to mind when reading this report. So all the way through, I had two questions, which is, who's at high risk for exposure? Are there people? And are there point sources other than wildfires, which could be usefully monitored and mitigated? So it was that context generally that was missing from this document in a way that it hasn't been missing in prior reviews. That seemed a little bit different for this document. So that's my general comment. It just raised a lot of questions. If wildfires spew this stuff out and humans produce it endogenously, what's the risk and what's the opportunity for risk mitigation?
Thank you, Dr. Messer, for that comment. We'll definitely add some information in the introduction for some context and relevance. And as Dr. Dodge had mentioned previously, it was detected near petroleum sources. So isoprene actually came on our radar for an assessment because it was detected in the SNAPS program. And SNAPS stands for Study of Neighborhood Air Near Petroleum Sources. So that kind of put it towards the top of our list so that we could get an IUR value for it so we could accurately assess the risk to the communities near those petroleum sources. So we can add that information into the report.
Yeah, that would be super, super helpful.
Great, thank you, Karen. Beata?
Yeah, I just put two reference sources in the chat box. on rubber and tire workers, and IARC has given them a #1 rating for carcinogenesis, but that's mostly there are hundreds of chemicals. There are PAHs, nitrosamines, all sorts of things, benzene, butadiene, that are exposures in these workers, and it's a big mixture, lots of cancer sites. So it's clearly human carcinogenic in the mixture as well, and that's what IARC evaluated. Maybe that's worth mentioning, and maybe those 2 citations could be used. Clearly in the environment, it's also a mixture, right? And how much it is just isoprene versus the combination with other carcinogens, we really don't know, but from the worker studies, at least we know that the whole mixture overall is a carcinogen. And I don't know, again, whether there are hotspots where these mixtures also are an issue, and where maybe the source that contributes to that mixture should be controlled. And whether you control butadiene, benzene, or isoprene may not be the question, but that the whole mixture will be controlled, and isoprene is one part of it. That's basically it.
Thank you. Yeah, that's an interesting point, right? When you've got these very complex mixtures, but we consider risk on an individual compound basis. But hopefully if you mitigate emissions of one, you're mitigating multiple emissions. Okay, thank you, Beata. Last but not least, Dr. Mike Kleinman.
Well, thank you. I first want to echo that I really appreciated the presentation, and the document is an extremely well-written document. I wanted to agree with Ahmad's comment on improving the way that the literature search was documented. Critical literature reviews are now becoming fairly standard, and the methodology is fairly straightforward, and I think it would make lend a lot of credence to the objectivity of this review to actually go through the process and show what were the search terms, how many articles were accumulated, how many were rejected that didn't meet the cut, that sort of thing, until you get down to the articles that are critical for what you're doing. So, I think I don't see a need to do that for this document, but I think going forward, that sort of methodology should be more firmly incorporated. The other comment I had, I also wanted to thank you for a very lucid explanation of the use of the benchmark dose methodology and how it's applied. I think that was great. I'm going to incorporate it in the lecture. So thank you for that. The other thing I think that's been alluded to is putting these values into context, especially in the context of the endogenous isoprene production. When you look at the information, I think it's on page 11, endogenous isoprene production, the steady state end tidal breath concentrations are on the order of about 100 parts per billion, which you need to put into context of how does that relate to ambient exposures, and why, if you put a couple of humans in a box, are they not at risk? It's sort of something you look at it without context. I think needs a little more explanation. And I think I'll stop there. Thank you.
Okay, thank you, Mike. Did any other panel members have any follow-up comments?
Oh, excuse me, Court,
Yeah.
I did have one other minor thing, and that was, you had, mentioned the missing minus sign in the properties of isoprene. And that was actually corrected in the, more recent draft that's on the website.
Ah,
So, oh, he is ahead of you on that.
perfect. Karen, do you have a comment?
Yeah,
Cool.
just to follow up on the context comment. I guess that's my hobby horse this meeting. I agree. With the ambient exposures and the I the endogenous exposure, I had to make a little spreadsheet and compute them all and put them all out to see how they compared to each other and see how they compared to the levels in the experiments. So it'd be helpful to do some of that work for us. And also, I forget which colleague made the comment, it would be helpful to put the final cancer slope factor or inhalation unit risk into context also, especially given Beata's comment that this chemical occurs in mixtures usually. I mean, we know the usual components in the mixture from an oil well or from a fire. And if those are the major exposure sources, then I think it would be very important to say whether this is likely the most carcinogenic species in the exposure or among them, or whether it's maybe a more benign one. I think it would be helpful to have some context there.
Thank you, Karen. Sorry, did you have your hand up for a second?
Yes, yes. What do you want from the members of the panel? Do you want written comments, or is what's in the transcript sufficient?
I'll leave that up to Awiha.
Yeah, this is Darren. We will get transcripts, and so we'll operate off that in terms of answering the questions from the SRP. But if you do have additional comments that you'd like to send to me in written form, I can look at those too.
Okay. And let me ask you for something as well. Do you have you must have the listing now, a huge, long listing of all the cancer slope factors for inhalation. Do you have that in a document? Could I get a copy of that, and whoever else wants one?
Yes, we do have that list. It's on our website, but we can also send you a copy of that PDF directly. It's a table that contains all our current cancer values.
Thank you. And I could print the whole document out myself too, if I wanted.
Yes.
Okay.
Yep.
Do you know the website?
It's on our website, but I can send it to you directly to save the time for searching for it.
That's very nice of you. Thank you very much.
Sure.
Okay, any other panel comments? All right, seeing none, we're going to take a break. Let's reassemble at 11:15, and then we'll have the informational item about computational toxicology from WEHA. So I'll see you all at 11:15.
Mm.
Okay, welcome back, everyone. Before we move on to our next item, I forgot to conclude the isoprene discussion with next steps. So given that the comments from the panel were significant but relatively minor in the sense of what the IUR value is, I'm going to suggest that OWIHA sends the revised isoprene document to the leads, me and Ahmad, and then we sign off on it. And that will be the SRP approval. Can I get a vote on this? So all in favor of my proposal? You just raise your...
I,
Aye.
Sorry, Mike, did you want to make a comment?
no, I was just saying aye.
Oh, you're saying aye. Okay, let's do the hands and I can count more easily. Okay, we got...
Gord, can I ask, would it be possible for the OWIHA to either mark or highlight the revised version, the changes that were made, so it would be easier for us to kind of go through the modification and figure out whether the amendments were made in response to the comments that
Yeah, that's been their standard practice. They'll give us a tracked change version of the document, so we can see exactly what has been changed.
Okay,
Yeah,
great.
which is very helpful.
Thank you.
Okay, so let's see, is everybody on now? So let me do the vote one more time with the panel. So all in favor of the leads approving the revised document? Did Mike, I already saw your hand before. Okay, so it looks like it's unanimous. Okay, so we'll do that. So Rima, if you could send it to me and Ahmad, and then we'll sign off on it.
Great. We will send it to you as soon as we complete all of the revisions that were requested.
Great.
Thank you very much.
Thank you. Okay, so our second major item today is an informational item from OWIHA on computational toxicology and their new approach methodologies. So OWIHA, as we've talked about in prior meetings, is developing expertise in what they're calling new approach methodologies, or NAMs, to support Cali EPA programs and regulatory activities. So NAMs are new toxicological testing and analysis methods that allow for informed predictions of biological effects for data poor environmental pollutants. The idea being you can develop a health guidance value without having animal or epidemiological data. There are several components to this effort, including creation of new toxicology evaluation sections within OWIHA, and developing collaborations with academic organizations with NAM's expertise on data poor compounds. The newly created section within OWIHA brings together expertise in toxicology, bioinformatics, toxicokinetics, and computational chemistry. So the item that we're going to have presented to us now is an overview of the NAM's work at OWIHA and the potential applications. So it's my pleasure now to introduce Anatoly Soshilov, who is the supervisor of the new toxicology evaluation section from OWIHA. Welcome, Anatoly.
Welcome, everyone. Let me start my presentation. And please let me know if you can see the screen, and you should see the first slide now.
Yes, looks good.
So I'm a senior toxicologist at AIHA, and today I will present on the use of computational toxicology and new approach methodologies on NAMS at AIHA. In my talk, I will describe new approach methodologies on NAMS and their use in toxicology and risk assessment. Next, I will summarize the NAMS-related activities at AIHA, including staffing the new NAMS section, academic collaboration on NAMS-related projects, and creating an expert panel for input to NAMS-related projects. In contrast to traditional approaches in toxicology, which analyze human epidemiological and animal toxicological data, new approach methodologies on NAMS use in vitro data, including information obtained from cell cultures, in silico data, such as predictions of binding chemicals to macromolecular targets, and even some alternative animal models, such as transgenic mice that are generated to increase sensitivity in specific assays. While traditional toxicological approaches employ animals mimic duration and route of exposure to humans, and therefore require a significant number of animals, NAMS are developed with the goal to reduce and replace animal use in chemical risk assessments. NAMS is an umbrella term that includes a variety of different approaches and methods, and this is a rather busy slide, so I'll just spend some time here. This can include computational modeling and read-across approaches in which quantitative structure-activity relationship models or QSARs, as well as physiologically based kinetic or PUPK and other types of models can be developed. Computational methods can include machine learning and read-across approaches, which utilize toxicity data for source or data-rich chemicals to predict effects for target or data-poor chemicals. A lot of NAMS work is done with cells in vitro in the form of 2D or 3D cell cultures that can be engineered into macrophysiological systems such as organoids or organs on a chip. This one, I don't know if you can see my pointer, this is an organ on a chip actually. Multiple cell lines combined on a single chip connected with the flows. Cell cultures are ideally analyzed with high throughput screening methods that can include different omics approaches such as genomics, transcriptomics, proteomics, and different advanced imaging techniques. The goal of NAMS implementation is to reduce and replace vertebrate animal use, and some alternative species such as fish were proposed for studies as a replacement. While genetic mouse models were developed to increase sensitivity and therefore to reduce the overall number of animals in experiments. Next, I'm going to describe two examples of NAMS used in risk assessment. Our first example is read-across. Read-across is an approach in which toxicity for a target or data-poor chemical is predicted based on similarity with a structurally related source chemical or chemicals. The similarity can also be based on toxicokinetic or mechanistic information that can be obtained from NAMS. In this particular approach, in this read-across framework, the formulation of the initial read-across hypothesis, identification and evaluation of the source chemical, and refinement of read-across hypothesis with the help of NAMS occur in an iterative manner, where newly acquired NAMS data may further inform the read-across hypothesis. NAMS data in this approach can also provide toxicokinetic and toxicodynamic insights. The next step in this framework is uncertainty assessment, and in the end, the overall approach allows for data gap filling in the risk assessment of the target data-poor chemical. Our second example is in vitro to in vivo extrapolation or IVIV method. Sometimes when no in vivo toxicity data is available for the chemical of interest, in vitro data, such as derived from cell culture, can provide dose response information on a relevant endpoint or combination of endpoints. The question becomes, how do we extrapolate the in vitro point of departure? In this case, it's AC, active concentration 10, to an in vivo equivalent. To do so, we assume that the observed concentration or equivalent, adjusted for cell culture effects, represents blood or organ concentration. Next, this assumed metric is converted to applied dose using a physiologically based kinetic model, with an example here. Such models imagine the body as a number of interconnected compartments and typically model absorption, distribution, and elimination of target chemicals as precise flows in and out of the system and between the compartments. In the end, the equivalent of in vivo dose response is produced that can be used for derivation of reference dose. Of course, this method comes with certain limitations that need to be carefully considered on a case-by-case basis. The need for NAMs in toxicology is increasing. This is because we are exposed to increasingly more chemicals that lack health assessments. We also become aware that we are exposed to more chemicals when new detection methods are used or detection limits of existing methods are lowered. New chemical alternatives are proposed that lack health data and require assessments as well. Some examples in this case are novel PFAS and disinfectant quaternary ammonium compounds, or QUACs. Finally, several initiatives at the federal and international levels are now underway that aim to reduce and replace animal use in toxicological studies. In this situation, NAMs are the main available method that can help with the health assessments of chemicals that lack regular toxicity data. Contrary to the possible perception that NAMs are a new and untried approach in chemical risk assessment, several agencies have been using NAMs data in routine assessments. For example, in monographs by International Agency for Research on Cancer, or IARC, NAMs make part of the mechanistic evidence stream, which is organized according to the key characteristics of carcinogens framework. Together with human and animal evidence streams, the mechanistic evidence stream informs the carcinogen classification of the chemical of interest. US EPA uses a read-across approach in developing provisional peer-reviewed toxicity values, or PPRTVs. This read-across method relies on 3 similarity domains for the target and source chemicals, including structural physiochemical similarity, metabolic toxicokinetic similarity, and toxicodynamic or mode of action similarity. To address the increasing need for NAMs in toxicology, in 2023, AIHA created a new toxicology evaluation sections, or NTS. This section works with Cal EPA BDOs, academic partners, and other stakeholders on assessments of data-poor chemicals. This section includes 5 newly hired staff, with 2 toxicologists, 2 chemical scientists, and 1 bioinformatics scientist. Our academic partnerships on new assessment methodologies include 1 contract with UC Berkeley that focuses on predictive methods in carcinogenesis, 1 contract with UC Davis that compares in vitro and in vivo effects for emerging pollutants, and 3 contracts with UC San Francisco that develop alternative methods in assessing developmental toxicity, as well as 1 contract with Texas A&M University that focuses on toxicokinetic and transcriptomic studies. As part of the proposed NAMs activities, NTS in cooperation with TAMU organized 2 toxicokinetic workshops that included presentations by academia, industry, and government agencies, followed by discussion of case studies relevant to our chemicals of interest. The first workshop focused on toxicokinetic tools in decision-making, and the second workshop focused more narrowly on NAMs tools in inhalation toxicology. Part of the proposed NAMs work at NTS is creating of NAMs Expert Panel, or EPRA, which stands for Expert Panel on Emerging Risk Assessment Approaches. This panel includes experts in relevant scientific fields who will provide expert advice and feedback to activities on NAMs. The current plan for the panel is to meet twice a year. It is not a mandated committee like SRP or SAP, and its input is not a substitute for peer review process. First EPRA meeting is planned for fall 2024. And to conclude, new approach methodologies on NAMs are becoming part of a landscape of tools for informed decision-making for data poor chemicals. And AIHA's efforts in NAMs space include creating new toxicology evaluation sections, fostering academic collaborations, and assembling an expert panel. Thank you.
That's great. Thank you very much, Anatoly. Panel comments? Okay, Karen, go ahead.
Yeah, very nice to see these new technologies brought into this area. These are technologies that we see in drug development in cancer. I'm familiar with a lot of them in that context, high throughput screening and computational biology, and these rapidly developing models, organoid models that are in use. And it's a very exciting area, a lot going on, rapidly developing, and I'm sure that there will be use cases that will come out of your work that'll be very, very helpful. So just a vote of enthusiasm for the effort. And then just a comment that where I'm familiar with using these technologies, drug development, they're preclinical work, and then it goes into progressively into animal models for confirmation and finally into human studies for confirmation. So just pointing out that that's the context in which we're used to seeing this kind of work. So that'll be our natural inclination to call for validation studies, you know, if there's a computational prediction. So just setting that up is what someone like me would expect to see. And then another comment that it seems like a particularly fruitful area might be in prioritization of this long list of chemicals. That's something that has come up before this panel, that there are so many chemicals out there. How are they being prioritized for study? And it seems to me that's an area where there might be a big impact from some of these technologies. And then they would feed naturally into more either future animal studies or epidemiologic studies that can have a confirmatory nature. So thank you.
Thank you for your comment.
Thank you, Karen. Beata?
Yeah, generally, I really, enjoy what is coming out of these technologies and all these data streams. And in epidemiologic research, I've been more and more using, omics tools. So I think they're very useful. But recently, EPA is reassessing several OP pesticides and has been using NAMs to excuse all EPI studies and more or less, invalidate what they've been showing in terms of neurodevelopment in children. And they have also been used to replace some of the more the older toxicology assessments. And I don't think they should be used in this way, but I don't know how we can guard against that, because they seem like such shiny, beautiful tools, and they can be very convincing in some way, but they should not replace the real model, which is human data, and certainly not the traditional animal studies.
Yeah, I think that points out the importance of validation, as Karen mentioned.
I also would like to point out that any study or health assessment that we would develop that's applicable to air pollutants would eventually come up in front of this panel. So this would be the discussion where applicability of this method would be relevant.
Yeah, that's a good point. Other panel comments? I would just like to echo what Karen said, and I know I've said this at prior meetings as well, that I really think this is an enormously important effort, given that we have, I believe, hundreds of toxic chemicals listed on Appendix E for the hotspots, and we can get through maybe 2 a year. So we need a new approach that really gives us at least, rough estimates of health guidance value, so that we can then maybe focus the animal studies on the most important chemicals that are identified using NAMs. So yeah, I think this is really important. I did have one question for you, Anatoly. Can you talk a little bit about the timeline? When do you expect to start having health guidance values, some initial ones that can be validated?
We are currently working on one chemical to supplement assessment that's been performed in water. And so our original strategy is to develop assessments in parallel as a means to validate the approach, and not necessarily as our, well, definitely not as our proposed freestanding reference value. So we do pay a lot of attention to validation part. And that assessment should be coming out within a year, I would imagine. So that would be the first example where we actually producing something that goes into an existing regulatory document.
That's
And
great.
that chemical is Anatoly, what is that chemical?
I don't think I can say that. It's one of their chemicals that a water board requested to develop a notification level for.
Can you give us a chemical category? Is it an organochlorine?
It's PFAS. So all the chemicals that have been recently requested by water board belong to the PFAS class.
PFAS, thank you.
It's one of the chemicals where there is some data, but it definitely helps to analyze all available data to strengthen the assessment.
Yeah, great. Karen?
Yeah, this, NAMs is such a broad term that there are lots of different ways it could be useful, and some of them are very different. So I imagine you can really help with insights into mechanism of action that can then give a sharper idea of risk, either from the step from one species to another, or in different exposure levels, or of related compounds. And those are sort of specific studies like you're describing here. And I think very targeted studies that you could do could be very useful and fill in gaps. That's a kind of application that I think many of us, if we saw the details, would be fairly comfortable with. I think what we would be less comfortable with is sort of a de novo study that stands in for any animal studies. And then the idea of ranking these chemicals, or having a risk scoring system somehow for the long list of chemicals that's available, that's kind of a different animal or a different project. So just encouraging your group to put some thought into that kind of project, sort of a broad risk assessment or prioritization or scoring study.
Noted.
Yeah, that's a very good point. Yeah. Any other comments from the panel? Mike?
Yeah, I think I want to, amplify the idea of the validation, and that might be one of the first tasks your expert panel could take on, is identifying some compounds where you have enough data from the traditional toxicology and the new methods to actually do a good validation that'll provide a lot more confidence in the applicability of the method. But I see this as being extremely useful in enabling us to fill out sort of an adverse outcome pathway for given chemicals, starting with molecular mechanisms and working our way through to actual organ effects in multiple species. The other comment I wanted to make is that despite the fact that it's very easy to look at one chemical at a time, we're all exposed to mixtures. And I think some effort should go into evaluating how mixtures would play out in this framework. Thank you.
I agree 100%. And then there's just no chance that we would get all the toxicity studies for mixtures. So once you start approaching analysis of mixtures, you need to understand what is happening, what's the mechanism. So NAMs again help. They even help us with traditional toxicity methods, providing better sort of understanding of the mechanism that can inform assessments.
Yeah, that's great. Any other panel comments? Okay, if not, thank you very much, Anatoly. We appreciate your presentation.
Thank you.
The final agenda item is consideration of administrative matters. First, look ahead to our next meeting. We're going to have 2 items soon, hopefully before the end of this year. The first item is Blueprint 2.0 from OCAP and CARB, where we've received an informational presentation on that at our prior meeting. And then we're going to have a health guidance value on 1,4-dichlorobenzene from OEHA. It's possible that hybrid meetings such as this one, where we all get to stay at home, might not be allowed next year. So we're going to try to schedule the next SRP meeting before the December vacations. So Arash is going to be reaching out to folks with the panel soon so we can get that on our calendars. Next informational item, I just want to acknowledge again that we have 4 panel members who have ended their terms. Really appreciate your many years of service. And I really, really appreciate your continued service on the panel as we wait for replacement members. So, we need a quorum to have an official meeting. That's 5 members. And with 4 retired members out of 9, it doesn't give us any leeway. So I really appreciate the panel members whose terms have officially expired continuing to serve on the panel. Yes, sorry, Paul?
I think you may want to ask guidance on the minutes, how the minutes should reflect that wording. Because if you say our service is expired, we actually have we shouldn't even be here. So I think what you want to say is that our term would have lapsed save for our continued participation, or whatever the technical term is.
Yes, good point. That I should have spoken a little more precisely. The terms are officially over, but you can continue to serve officially until a replacement has been named. So you're still officially members of the panel, although your nominal term is over. So I appreciate your service. The last thing, one more just note about that. So the process has started in terms of identifying new members, but no one has yet been selected. So we don't have replacements yet. The last item of business is a tribute to Paul. So it looks like he may be trapped in a one-room cell, but I'm sure he's got some retirement location that we don't know about. So I'm going to read a statement from the legislature acknowledging Paul's many decades of service to the state and service on the panel. So CARB staff have come up with a resolution that was supported by 2 assembly members and 1 state senator that I'm going to read now. So sit back, get a beverage, maybe some snacks as I read this epic poem to Paul Blanc. Okay, here we go. So this is dated August 9th, 2024. This is a member's resolution by the Honorable Scott D. Wiener, 11th Senatorial District, the Honorable Matt Haney, 17th Assembly District, and the Honorable Philip Y. Ting, 19th Assembly District, relative to commending Paul D. Blanc, MD. Whereas Dr. Paul D. Blanc, professor and endowed chair in occupational and environmental medicine at the University of California, San Francisco School of Medicine, will be concluding his remarkable 26-year tenure on the Scientific Review Panel on Toxic Air Contaminants, and it is appropriate at this time to highlight his many achievements and extend to him special public recognition and commendations for his professional leadership. And whereas, first appointed to the Scientific Review Panel in 1997 by the Senate Committee on Rules, Dr. Paul Blanc has held continuous membership on the panel, which is charged with evaluating substances proposed for identification as toxic air contaminants by the California Air Resources Board in coordination with the Office of Environmental Health Hazard Assessment and the Department of Pesticide Regulation. And for 26 years, he has provided his expertise in reviewing risk assessments, guidelines, and other documents to better characterize and reduce the risks of toxic air contaminants. And whereas throughout his academic career, Dr. Blanc has demonstrated extensive accomplishments in research and contributed significantly to studying asthma and chronic obstructive pulmonary disease in relation to workplace and environmental factors. And he has published more than 400 peer-reviewed articles, authored 2 books, and served as editor-in-chief of the Journal of Occupational Medicine and Toxicology, in addition to serving as chief of occupational and environmental medicine at UCSF. And whereas, honored with many accolades and awards, Dr. Blanc has received the Yaroslav Tysinger Medal from the Society of Occupational Medicine of the Czech Medical Association, Excellence in Education or Research in Occupational and Environmental Medicine Award from the American College of Occupational and Environmental Medicine, and Excellence in Interprofessional Teaching Award from the UCSF Program for Interprofessional Practice and Education. And whereas, contributing to research programs and policies in the United States and around the world, Dr. Blanc has served on multiple national and international panels, including the United States Environmental Protection Agency Clean Air Scientific Advisory Committee's Carbon Monoxide Review Panel, and the Danish Working Environment Research Fund's Occupation and Chronic Obstructive Pulmonary Disease Expert Review Panel, among others. And whereas, as the lead reviewer of numerous health risk assessment guideline documents, Dr. Blanc helped to facilitate the establishment of many health values used in the preparation of health risk assessments and identification of toxic air contaminants, such as chloropicrin and diesel particulate matter, that led to efforts to protect public health. And whereas, having served on the Scientific Review Panel for 26 years, Dr. Paul Blanc has played an integral role in the evolution and implementation of California's air toxics program, which has given Californians the opportunity to live in communities with significantly reduced concentrations of toxic air contaminants. Now, therefore, be it resolved by Senator Scott D. Wiener and Assembly members Matt Haney and Philip Y. Ting that Dr. Paul D. Blanc be honored for his extensive contributions to the Scientific Review Panel on Toxic Air Contaminants and extended sincere best wishes for success in the future. Dated this 16th day of August, 2024, Honorable Scott D. Wiener, 11th Senatorial District, Honorable Matt Haney, 17th Assembly District, and Honorable Philip Ting, 19th Assembly District. So with that, Paul, thank you very much for your 26 years of impressive service. And we will miss you on the panel. You can now have a rebuttal if you would like.
Well, I'm glad that nobody from OEA said anything about making them cry in the past. I haven't done that in a while, so.
All has been
maybe-
forgiven.
And just a brief moment to think fondly of Dr. John Freund's, who was my mentor and friend, and whose memory will be a blessing.
Yeah, well, thank you very much for all your work over these decades, Paul. We really appreciate your input, and the state of California really appreciates your help.
You're most welcome.
Anyone else want to roast Paul?
I just want to mention that this is maybe why we can't replace panel members, because how would we find someone like Paul?
It's a good point. You've made yourself irreplaceable, Paul.
Yeah, yeah.
Mike?
Yeah, I just want to thank Paul because over the years that I've served on the panel as a co-panelist, Paul, I have learned so much from his approach to toxicology and his extremely acute understanding of how the mechanisms of various compounds interact. I think it would be impossible to replace. So I'd like to thank you for all the things you've taught me.
That's very kind of you.
Ahmad?
Yeah, I just want to echo and thank Paul for his really lifetime contribution to the panel. And I want to just say that it has truly been an honor to serve on the panel with you and learn so much from you, particularly the meticulous way of you reviewing the documents and commenting on them. And it has truly been educational, at least for me. And thank you for that.
Oh, you're welcome.
I think Rima would like to address Paul making members of a WEHOC cry.
Well, I'm new here, so I haven't seen anyone cry, and I haven't heard the stories, but I believe Dr. Krishnan would like to speak.
Yeah, I'm Kanan Krishnan, Assistant Deputy Director at OEHA, Scientific Programs. I just want to thank you, Paul, for the wonderful contributions over the years and your enthusiasm, passion, rigor, and the guidance you have provided us over the years. You know, I have had the opportunity to listen to you during the last couple of years since I got on board here at OEHA. Thank you on behalf of Lauren, who has retired now, and on behalf of all of us at OEHA. Thank you.
Thanks. I'd also like to acknowledge our court reporter today and all of our court reporters at all of these meetings, and wishing that none of them got carpal tunnel from what we've done to them, but that may not be possible. I mean, it's possible for me to thank them, but I don't know if it's possible for us to have not caused that.
Jim is very tough. I think he's making it all work. But I second your thanks for the court reporters and all their tireless work on this. Okay, so that then concludes our meeting, unless there are any final thoughts or questions. Okay, great.
Thank you.
So we do need a motion to adjourn, but actually before we get to that, Paul, I forgot to ask you, so you've officially retired, correct, from UCSF?
Yeah, I'm doing a little bit of callback, and I'm currently working on a book project, which is why I'm calling in from the National Library of Medicine.
Ah, that's where you are. Okay. Yeah, I knew you'd be busy. I just didn't know with what.
Yeah.
So good to hear.
Yeah.
Yeah. Okay, with that, I'm looking for a motion to adjourn.
So moved.
Excellent. Second,
Second.
all in favor? Mike, you want to keep going? No. Okay, you're ready. Okay, we have unanimous. Thank you very much, everyone. Thank you, Arash, for organizing. And Paul, thanks again and
Oh, you're welcome.
congratulations. Yeah. All right. Have a great weekend, everyone.
Goodbye.
Bye.
Bye.
Thank
Thank
you
you,
all.
everyone.
Bye.
For the members of the public, we will have the recording available in the next week, and the official transcript for the public as well as OEHA will be ready in 2 working weeks. Thanks everyone for coming, and goodbye.